Okay. This is the 2016 A/B test. Continued. The table above gives values of f, f prime, g, and g prime for selected values. If h is equal to f of g of x, then what's the value of h prime of 1? Well, h prime of x would be, this is the chain rule in its most sort of generic form here. So the chain rule says if you have like a composite function, then the derivative would be f prime of g of x, and then times the derivative of what's inside. We had problems like this back in, way back in section, I guess, 3.6? Is that the chain rule, or is it 3.5? 3.5 or 3.6. I think 3.5 might be trig functions, and then 3.6 is the chain rule. Could have those backwards. But in your notes for the chain rule, this is actually how I presented it to you, that the derivative of a composite function, you take the derivative of the outside piece, leave the inside alone, and then multiply by the derivative of what's inside. So h prime of 1 would be f prime. I'm not going to try to do too much in any one step here. Just going to be careful. F prime of g of 1 is 3, right? G prime of 1 is -2, and then f prime of 3 is 7. That's -14. We had some questions like that on the 3.536 quiz back then. Let y equal f of x be the particular solution to this differential equation with the initial condition this. Which of the following is an expression for f of x? So we want to solve it. So separation of variables, got to move the y to this side. It's going to move up, and then the dx over here. Then we take antiderivatives. Antiderivative of that is y squared over 2. I'm not going to put the plus c here. We move the plus c over here. This is very recent stuff for us, so it should be pretty sharp on this. So that would be this. Going to multiply through by 2. And then I'm going to solve for c. F of 0 is equal to -2. So f of 0, when I plug 0 in here, for x, get the y is -2, right? That's x, that's y. So c is 4. So it looks like x, the square root of x squared plus 2x plus 4. Right, no, 22 is D. Hold on a sec. Oh. So this, when we solve this, it's y is equal to plus or minus the x squared plus 2x plus 4. And how do we know if it's the plus or minus? We look at this. If f of 0 is going to be -2, then it's got to be the -1 right here, because, well, you can just plug in that 0, right? We're going to get a negative there. So it's not this, it's this one. That's tricky. So because of that plus or minus, I probably would have missed that. Oh well, 29 out of 30 ain't bad, right? Let R be the shaded region bounded by the graph of y equals the square root of x, the line y equals x minus 2, and the x-axis is shown in the figure above. Which of the following is the volume of the solid generated when R is revolved about the x-axis? Okay, this is a little bit tricky because this region it's kind of defined in two different ways. Here, it's just the square root of x. So for this part of it, remember when we do volumes rotating things around the x-axis, it's pi r, which is the function, squared. And if it's an area between two functions, then we have to do that. Sorry, we have to do that, right? Because like the outside one minus the inside one. That should not be there. But here, the g function has not come into play yet, so it's just the f function right up against the axis. So from 0 to 2, it's just pi times r squared, where the r, the radius of our cross sections, is just the square root function. And then from 2 to 4, I have the outside radius is the square root function minus the inside radius is x minus 2. So there's different ways you could write that. Let's see how ours did. Let's see, that looks the same as this, plus x squared. The square root of x squared is just x. This looks good right here. This one, I guess they just forgot to square that. So I think C is looking good. That's a little tricky because it transitions from being like right up against the axis. It's only defined by this, and then it's like in between these two. So you have to do like the outside radius minus inside radius game. So 23 is C. Ooh, that's a crazy looking limit. If you plug 3 into this, you get tangent of 3 minus 3. Tangent of 0 is 0. Over 3 to the e to the 0 is 1. 3 minus 3. Yep, that's 0 over 0. So it's non-existent, right? No, because 0 over 0 is an indeterminate form. So we have to do L'Hopital's rule. There's no other way of doing this. There's no other like factoring and canceling, or it's not the definition of the derivative. This is straight up L'Hopital's rule. So let's see if we can get it to resolve with that. What's the derivative of tangent of x minus 3? It's secant squared x minus 3. And then on the bottom, what's the derivative of this? Derivative of 3e to the x is 3e to the x minus 1. Okay, well, let's try again. If I plug 3 in here, what's secant squared of 0? Now secant is just the cosine function upside down, and the cosine of 0 is 1. So that is actually just a 1 on the top. And whatever happens on the bottom, this is going to be done because I'm not getting 0 over 0 again. So here, if I plug 3 in on the bottom, I get 3 times e to the x e to the 0. So that's 3 minus 1 is 2. So it is 1/2 by L'Hopital's rule. Number 25. F be a function with first derivative defined by this. And right off the bat, when you see something with a monomial in the bottom, you can simplify that. That's f prime of x is equal to 3x squared divided by x squared is 3 minus 6x to the negative 2. That is a much more calculus-friendly way of writing this. You can't do that kind of simplifying when the thing on the bottom has like a plus or minus separating different terms. I know some people have bad algebra habits where they try to cancel things out in this way. But if you just have a monomial in the bottom, you can divide through by it. Okay, it's known that f of 1 equals 9. This smells like fundamental theorem. Oh no, it's a mean value theorem thing. So what value of x in the open interval satisfies the conclusion of the mean value theorem for f on this closed interval? What does the mean value theorem say? It says that average slope is equal to actual slope, and actual slope is the derivative. So average slope is just like old school slope, where we do rise over run, and the actual slope is the derivative, which is this. So I guess I'm going to use this version of it. Let's see, subtract the 3 over there. What are we going to do here? So x to the negative 2 is equal to 1/6. So flip over both sides. That means x squared equals 6. So x is the square root of 6. 25 is... Oh, no, it's telling me that 25 is B. What did I do wrong? Did I mess up my algebra here somewhere? Let's see. Let's back up to here. My slope, 11 minus 9 over 3 minus 1. That would be 2 over 2, which is not equal to 2. That's equal to 1. Sorry about that. That's my mistake. And then if I subtract 2, it's going to be minus 2. So that's going to be 1/3, and that's going to be 3, and that's the square root of 3. Sorry about that. That's funny that they had that answer there, just waiting for me to make that mistake. Oops. But we fixed it. All right. How about this? This is a tricky problem. I don't know that we did anything like this. So let's see. No, I think the way to do this, when you have, if you're looking at this one and you think, yeah, I'm not really sure how to do that. This is not something that, in my understanding, is really a part of the AB curriculum, but apparently, according to them, on this practice test, it is. So I think the way you need to do this, when you have this kind of polynomial and the degree on the top is higher, if you want to have a chance of cracking this thing, you have to do long division here to simplify this. And if you're thinking to yourself, whoa, haven't done that in a while. Yeah, you haven't, you're right. So x plus 2 goes into this. The way this game works, got to put an x there, you got to put whatever goes here, that when we multiply, you get the same thing, so that leading term cancels out. We'll see where this leads us. I think that this is the only way to do this problem for us. X, what do I have to put here? I'd have to put a minus 3, so that when I multiply here I get minus 3x, and then it's minus 6, subtracting that gives me a remainder of 1. So what that means is that this is the same as x minus 3 plus 1 over x minus 3. And now that we have it like that, I can do it. Yeah. Well, sorry I never gave you any problems like this one. Not something that happens in our book, like in any kind of place where we would have hit it. So antiderivative of x is x squared over 2 minus 3x plus the natural log of x minus 3 from 1 to 2. Why is it natural log here? Because it's just x to the first power. And then plug in the 2. 2 squared over 2 is 2 minus 6 plus natural 2 minus 1, 2 minus 3 is negative 1, absolute value, that's the natural log of 1, which is 0. I'll get rid of that in a sec. Minus, what do I get when I plug 1 into all this stuff? 1 minus 3 is 2, so that's natural log 2. Oh, I'm not liking the look of this. It's not looking like any of those answers. Let's see where this goes. That's 0, so negative 4 minus, that's plus 3 minus a half, confusing myself. That's negative 2.5 right here, but that's plus, do that, and then minus natural log 2. Yeah, that's not anything like this. Okay, let's back up for a sec, see if we can figure out what went wrong.
Chastity Southers, please report to the main office. Chastity Southers, please report to the main office.
Well, now that we've got that taken care of, so x times x is x squared, x times is plus 2, subtracting that, that's minus 3x, and then we drop that, and then minus 3. Oh, that's the problem. I used the wrong thing. Sorry, the denominator is this, not the x minus 3. Sorry about that. So that's going to be x plus 2. So, okay, that doesn't change that much. That doesn't change this, or this. So that negative, that should still be minus 3 halves there. Sorry, I don't know why I scribbled that. A minus 4 plus 2.5 is still minus 3 halves. And now, these things, when I plug the 2 into this, that's natural log of 4, and then that's going to be natural log of 3. So natural log 4 minus natural log 3, you know your logarithm rules, that's natural log 4/3. All right, got away with that, by the skin of my teeth. Sorry, it was because I copied down the wrong denominator there. Okay. Hemispherical water tank shown above has a radius of 6 meters and is losing water. Area of the surface of the water is this. When h is 3 meters, depth of the water is decreasing. The water level, the height is decreasing. That's dh dt, negative 1/2. What's the rate at which the area of the water's surface is decreasing with respect to time? This is related rates. Related rates, section 3.737. So related rates always starts with an equation, something usually from geometry, and then we take the derivative of it with respect to time. 12 pi is just a constant, so it's 12 pi. The derivative of h is dh dt minus 2 pi, right? The 2 is coming out to the front, times h dh dt. So all the derivatives are just like exactly what they would be, except every single letter gets a d whatever dt, right? dA dt, dh dt, dh dt. And then I want to know what's dA dt when dh dt is negative 1/2 and when the height is 3. So this is dh dt is negative 1/2, 12 pi times negative 1/2 minus 2 pi. The height is 3 times dh dt, which is negative 1/2. So let's try to clean that up. That's going to be 6 pi negative, and then 2 negative signs going to be plus. The 2 and the 1/2 cancel out, 3 pi. So that looks like negative 3 pi. So it's decreasing 3 pi square meters per minute. Right? And they asked what's the rate that it's decreasing at, so that's why the negative sign is already kind of baked into the way that they stated that there. Number 28. Consider a triangle in the xy plane. 2 vertices of the triangle are on the x-axis at 1, 0 and 5, 0. Okay? And the third vertex is on the graph of y equals whatever this function looks like, for somewhere between 1/2 and 8. So who knows what that looks like? What's the maximum area of such a triangle? Well, the base of the triangle is going to be this, and I don't know what that curve looks like, but let's say it just looks like this, right? The other vertex is on this. right? So it's at the point x, comma, y, which is this, natural log of 2x minus 1/2 x plus 5. So let's see, what's the area of this triangle? It's 1/2 base times height, right? And this is the height, the y-coordinate. And 1/2 the base is 4, so 1/2 base times height, I'm going to do my work down here, is 2 times this whole thing. I guess I could distribute that now, but I want to do too many steps at the same time. This is the area of the triangle. So how do you find the maximum area? This is kind of like one of those, like an applied max-min problem like we did in section 5.5. If you're looking back to like wherever did you do something like this. So I'm just going to go ahead and simplify, or at least distribute this 2. And then to find the maximum or minimum of something, I'm a calculus student, I know how to do that. Take the derivative and set it equal to 0. So the derivative of 2 natural log 2x is 2 times 1 over 2x times the derivative of what's inside, minus 1, that goes away. And I'm going to set the derivative equal to 0. That is 2 over x minus 1 is equal to 0, so x would be 2. But we're looking on an open interval here, closed interval rather, so I have to check the endpoints. My maximum area could be at 1/2, it could be at 2, and it could be at 8. Right? These are the x values. So I need to check them. What it means to check them is to plug them into the area formula that we have here. You can plug it into this or this, and see what the areas are. So here, if I plug in 1/2, I get 2 times the natural log of 1, which is 0, minus 1/2 plus 10. Sorry, more math. And then if I check 2, I get 2 times the natural log of 4 plus 8 and then at 8 I'm going to get 2 times the natural log of 16 plus 2. And we need to be able to figure out if, like, what's going on here, what's bigger than what. And that's kind of, I don't know, that's fairly tricky. I guess I'm trying to think from their point of view how they would want you to think about these numbers. You know that E is like approximately like 3-ish. It's a little smaller than 3. So the natural log of 4, the number you'd have to raise E to get 4, it's a little bigger than 1 anyway. So this is definitely bigger than 9.5. And it's got to be a maximum or a minimum. So it must be going from 9.5 up to this and then back down to that. That is pretty tricky. And did they give the other things as choices? Yeah, they did. I mean, there's the other things as choices. So how are you supposed to know that this is smaller? Well, if E is about 3, then 3 squared is about 9. So this number is between like 2 and 3. So if that was 3, which is like the cap on that, it'd be 2 times 3 is 6 plus 2. That's like 8-ish. So that's tough to figure that out. You have to have a pretty good number sense of what's going on with those natural logs to be able to get that. But C is the correct answer. 29, function defined by this. If g is the inverse of f and g of 2 is equal to 0, what's the value g prime of 2? So these are inverses of each other. So this is F and this is G. Then if G has the point 2, 0 on it, then F has the point 0, 2 on it. And that means that F prime of 0 is the upside down of those are equal to each other, right? The slopes are upside down of each other at those related points. So I've got F, so I can find F prime. It's 3x squared plus 4. And F prime of, what should I plug in here? I should plug in 0. So that's 4. And that means that at the related point on the inverse, the slope would be 1/4. Those are super easy if you can just keep that straight, right? Organize your information. If 2, 0 is on the g function, then 0, 2 is on its inverse. Take the derivative, plug in the 0, flip it over. All right, speaking of problems that are easy, this is not one. This is, what we have to recognize here is that these expressions are little like sums of rectangles. So that's kind of a tricky thing to do. Like way back when, I don't know if you remember, in the early days of chapter 6, we defined an integral to be the limit of the sum of a Riemann sum of a bunch of rectangles. So there's different ways to think about this, I suppose, but here's what I'm going to recommend. If you were actually going to do a Riemann sum for this, from going from 2 to 5, the easiest thing to do would be to bust it up into 3 rectangles, right? So if you did that, 2, 3, 4, 5, and you plugged in 2, you get like 2, 4, and 3, 9, and then this would be 16. This is not drawn to scale, obviously. And then you could make some rectangles. You could make left rectangles like this, or you could make right rectangles, and you could get a sum like that and get an approximate area. So what I'm going to do is I'm going to go from 1 to, I'm not going to go to n, I'm going to go from 1 to 3, and I'm going to see which one of these expressions matches up to give me a rectangular sum that makes sense here. Okay, so for A, if I'm just going from 1 to 3, so n is equal to 3, then k is going to tick from 1, 2, 3. So if I plug in 1 for that, I get 2 plus 1/3 squared times 1/3. That's what I get when I plug in 1, plus 2 plus plugging in 2 for k, and then plugging in 3 for k, so 3 over 3. Okay, now that I see that, maybe we can kind of see what's going on, right? We can see that, okay, this is trying to be like the height of a rectangle, right? Plugging something in, and then this is trying to be the width of a rectangle. But it really kind of messed up, this one, because this really needs to be 1 for the width of my 3 rectangles, and this we would need to be like plugging in like 3, 4, and 5, not 2 1/3, 2 2/3, and that. So it's kind of like that really, these needed to be like 3 times bigger, and this needed to be 3 times bigger. So I'm looking at this last option and thinking that that might be good. So let me just try that. If I plug in k equals 1, 2, and 3, remember that n is equal to 3. So then I have 2 plus, when I plug in 1 for k, I get 3 over 3 times 1 plus 2 plus, when I plug in 2 for k, I get 6 over 3. All those just cancel out, right? And times 3 over 3, and 2 plus 3. And you can see that is exactly like 3 squared times 1, 4 squared times 1, and 5 squared times 1. So this is doing a Riemann sum thing for whatever you make that top number. And if you let n approach infinity, then that's actually going to get closer and closer to the actual integral. So that's the right answer choice there. Tricky one. That was, in my opinion, I think that was a fairly tough practice test. So if that didn't go super well for you and you're taking the AP test, I would not take that. Don't take that too hard.